Welcome to This Explainer. Today, we're going to completely demystify algebra for elementary students. You know, when most of us hear the word algebra, we probably picture high school classrooms, confusing equations, and just memorizing formulas with a bunch of random letters. But what if I told you that algebraic thinking actually starts way earlier? And it's honestly far more intuitive than you might think. We're drawing from the fascinating insights in Chapter 15 of Teaching Student-Centered Mathematics to uncover how students in grades 3 through 5 actually begin to master this foundational logic. So, let's just dive right in.
I want to start by challenging your own preconceived notions of algebra with a really relatable everyday mental math problem. Think about this for a second. How would you mentally solve 49 plus 18? Don't write it down. Just think about what your brain does automatically to find that answer. If you're like most people, you probably didn't perfectly visualize carrying a 1 in your head, right? Instead, you likely made a quick adjustment. You might have bumped 49 up by 1 to make a nice round 50. Then you compensated by subtracting 1 from the 18, making it 17. Finally, you added 50 plus 17 to get 67. Now, here's what's really interesting. This flexible manipulation of numbers, decomposing and recomposing them, means you are actually already thinking algebraically. The source text gives this exact process a specific name. It's called Generalized Arithmetic. It's defined as noticing patterns that hold true in algorithms and mathematical properties and reasoning quantitatively about them. By shifting numbers around to make mental math easier, you're utilizing the foundational structure of our number system. You aren't just doing arithmetic anymore, you're generalizing it. And that foundational mental flexibility, well, that is exactly what algebraic thinking is all about. To show you how digestible this topic really is, we're going to unpack the 4 core pillars of algebraic thinking today: generalized arithmetic, the meaningful use of symbols, explicit structure, and patterns in functional thinking. Section 1. Generalized arithmetic. Finding patterns in arithmetic. The crucial idea here is that even the most basic arithmetic situations can be extended to find broad generalizations about how numbers work. The text uses a wonderful story to illustrate this. Imagine 10 guinea pigs, hopefully well-behaved ones, are housed in 2 different cages in a classroom. Students are asked, what are all the different ways that 10 guinea pigs can be distributed between these 2 cages? At first, students just list the combinations, 9 and 1, 8 and 2, but then educators guide them to describe this relationship. A student might say, subtract from 10 what's in the first cage, and you get what's in the second cage. We write that out in words, and eventually we condense it down to a generalized equation. 10 minus n equals our unknown amount. Just like that, we've moved from a concrete word problem about fluffy pets to confidently using a variable. Section 2. Meaningful use of symbols. The true meaning of symbols. A huge roadblock for students in algebra actually isn't the complex math. It's a deep misunderstanding of the symbols themselves, particularly the equal sign. For so many students, the equal sign just acts like the enter button on a calculator. This is called the operational view, basically thinking the equal sign just means do something, or the answer comes next. So if they see an equation like 8 plus 4 equals blank plus 5, they might just write 12 in the blank simply because 8 plus 4 is 12. But the text emphasizes that students absolutely must develop a relational view. They need to see the equal sign as a symbol that shows a relationship and a balance between 2 distinct calculations. It's not an action, it's a statement of equivalence. Using a physical 2-pen balance in the classroom serves as a super powerful visual anchor for this relational view. When students see that the expressions on either side of the equal sign, like 3 times 4 plus 2 on one side and 2 times 7 on the other, both evaluate to 14, the scale balances. If you add or subtract a value from one side, you have to do the exact same thing to the other side to keep it balanced. This entirely shifts their understanding from just finding the answer to maintaining a balanced relationship. Now, variables are the other notoriously misunderstood symbols. A lot of students think a variable is just a placeholder for one exact hidden number. But the text outlines 3 distinct ways elementary students experience variables. First, as a specific unknown, like in the equation 8 plus n equals 12. Second, as a pattern generalizer that is true for all numbers, like a times b equals b times a. And third, as quantities that vary jointly. Think of the equation y equals 3x, which could represent buying x items that cost $3 each. As the number of items changes, the total cost changes right along with it. Section 3. Explicit structure. Uncovering math's hidden structures. When we make the hidden structural properties of our number system explicit, we're giving students incredibly powerful tools for efficient computation. The text shares a fantastic micro-narrative of this in action. A teacher gives students a series of multiplication problems. First, solve 35 times 52. Then, solve 52 times 35. The teacher simply asks, "What do you notice?" The students realize the answers are exactly the same, which saves them half the work on the second problem. Then the teacher asks the crucial algebraic question, "Will this always be true?" Through examples, the students confirm that numbers can be multiplied in any order. The teacher then guides them to write this pattern using symbols. A times B equals B times A. They are uncovering the commutative property, not by rote memorization, but by recognizing the explicit structure of mathematics.
The crucial point here is captured beautifully in this quote from Empson and colleagues, highlighted in the source material. To understand arithmetic is to think relationally about arithmetic. When students stop just calculating blindly and start looking at how numbers relate to each other, they're doing true mathematical reasoning. This relational thinking is literally the key to true mathematical proficiency.
Section 4. Patterns and Functional Thinking. Exploring Patterns and Functions. Algebraic thinking involves learning to expect, see, and use patterns across all areas of math, whether we're looking at numbers, shapes, or real-world contexts. One of the absolute most engaging ways educators introduce this is through the concept of a function machine. It is highly playful. You drop a number into the input at the top, a hidden mathematical rule is applied inside the machine, and a predictable output emerges from the output at the bottom. This perfectly models joint variation. For every unique input, there is a specific, unique output based on a continuous rule. To determine that hidden rule, students track these growing patterns in a simple input and output chart. If a 3 goes in and a 7 comes out, maybe the rule is +4. Let's test it. If a 4 goes in and 8 comes out, yes, it works. What about 10? The output is 14. By observing the numbers that are paired up, students get to act as mathematical detectives, determining the underlying functional relationship completely themselves. They're actually working with algebraic functions, just without the complicated high school notation. And this doesn't just happen with numbers on a chart. It connects beautifully to geometry too. Imagine building rows of square pattern blocks and finding the perimeter of the growing shape. One square block has a perimeter of 4. 2 adjacent square blocks have a perimeter of 6. 3 blocks have a perimeter of 8. By physically building these shapes, students can concretely model functional relationships, tracking exactly how the perimeter grows in relation to the number of blocks used. They can even graph this data on coordinate paper. Wow, we have covered a lot of ground today, looking at how elementary students transition from concrete arithmetic to the generalized relational thinking that defines algebra. We've seen how rearranging mental math, balancing equations, noticing structural properties, and identifying growing patterns are all deeply algebraic acts. So I want to leave you with this thought. Now that you know these 4 pillars of algebraic thought, how will it change the way you approach everyday problem solving? Are you going to start noticing the hidden structures and mathematical patterns in your own life? Thanks so much for joining me for this explainer, and hey, keep thinking relationally.